Let's continue with the second exercise. Here we have to prove proposition 7.1.11, which, if you recall, gives us the basic properties of sums over finite sets and which mirror the corresponding properties of finite series, which we have already proved. And there is a hint also. The hint says this is not as lengthy as it may first appear. It is largely a matter of choosing the right bijections to turn the sums over sets, that is finite sets, into finite series and then applying lemma 7.1.4, because the properties of sums over finite sets that we have to prove here, they have their corresponding finite series versions already proved in this lemma. So we have this lemma at our disposal. So that is why it won't be as lengthy. Okay, so let us see the solution. And in the solution, just like what we did when we proved this lemma, we are going to recall the parts and follow them up with the proof of that part. Okay, proof of the parts will come after the statements. So the part A is this: if the set X is empty, and if f is a function from X into R, the set of real numbers. This is a function, i.e. f is the empty function with the range R. There is no other choice. We know that there can only be one empty function whose range is a given set, and the domain, of course, is the empty set. Then this was the conclusion of part A. This sum has the value 0. Okay, so let us now prove this. What we are going to do is, it's already laid out here. In most of the cases, we just have to find an appropriate bijection, and which will give us the meaning of this sum, and from that meaning, in most of the cases, the result will directly come out. Consider the bijection G from the set of all natural numbers I satisfying these inequalities into X. Note that the domain of G is also the empty set, because no natural number I satisfies these two inequalities simultaneously. And just like this empty function, this is also ultimately another empty function, and in fact here the domain, of course, is empty and the range is also empty, and that is why this G, unlike this F, is a bijection. We already know that any empty function is an injective function. The condition for injectivity in case of an empty function is vacuously true, and when the range is also the empty set, then we get a bijective empty function. There is naturally, you can see only one such function. In this case, the condition for ontoness is also vacuously true. That is, G is the empty function from this domain into this range. And let us also recall one more thing. The word range means the second set, the set to which in which you will find the functional values. It does not mean the set of all images. Okay, that's not what we are meaning here by the word range. In the other terminology, which is somewhat old, the first set is domain, it is always domain, and this set is codomain. Okay, and in that terminology, range is the set of all possible images. But in this terminology, the new one that we are following here in this text, the first set is domain, the second set is range, and the set of all images, all possible images, is the image set. That's just it. Okay, now that we have a bijection like this, we can now use the definition of this sum using this bijection and have this. Then summation f of x as x varies over the set x is by definition equal to this finite series where the index I varies from 1 to 0. Because 0 is less than 1, by definition of a finite series, this is equal to 0. So that's how we get 0. So you can clearly see that we didn't have to in fact do anything. We have just simply applied the definition of a finite sum or a sum over a finite set, in this case where the set itself is empty, and we have found its value. That's just it. So this is part A. Then in part B, x becomes slightly larger. Instead of the empty set, x now becomes non-empty, but it has only one element. Let the set x consist of a single element, that is, x is a singleton set where the sole element of x is something, x naught, some object, and let f from x into R be a function. Now, unlike the previous case, now f is not a unique function because there is only one empty function, so we had only one possibility for f. Here, however, in spite of such a small domain, there are infinitely many possibilities for f, because you can choose the image of x naught under f to be any real number. So all the real numbers will give you, each real number will give you a different function. So now we have as many choices for f as there are real numbers. Then the result says that this sum is f of x naught. Okay, so let's prove this one also, just like the proof of part A. Consider the bijection. When we write a statement like this, consider the bijection, and then we write or define a function, it should be understood that either the function is known to be a bijection or it's extremely easy to prove that it's a bijection. If that is not the case, then we don't boldly claim in the beginning itself that we are writing a bijection. We just simply write, consider the following function. Then we show that it's a bijection, then only we write it's a bijection. But these functions, the empty function and the one that now I'm going to write, these are so easy to see that they are bijections, so we have decided to write like this. Because the range has only one element, the domain also has only one element, because then only it can be a bijection. And although we have written I here, but you can clearly see this I takes only one value, which is 1. That means g of 1 has been defined to be x naught. Then again, by definition of sum over finite sets, this now becomes, using this bijection, f of g of I, where now I varies from 1 to 1. And from elementary properties of finite series, we know that this finite series has the value f of g of 1, because the only value I takes, the index takes, is 1. And g of 1 is x naught, so that's how you get f of x naught. So this is part B, it has been proved. In part C, it's the substitution. There are two substitutions, part 1 and part 2. It's good to have names given to things. That makes it easier to remember the things. Let X be a finite set let f from x into R be a function, and let g from y into x be a bijection. So now two sets are there. X, already we always are having x and a real valued function on x, where x is a finite set, but now additionally we also have another set y, and because there is a bijection g between x and y, so y is also a finite set and it has the same number of elements as x. Then this happens. this sum becomes equal to this sum. Okay, does this make sense? You see for a moment. G takes us from y to x and then f takes us from x to r. So that means this f of g of y is ultimately a real number. So it makes sense. And because this variable y is varying over a set capital Y which is also finite, so we are adding finitely many real numbers. That's what it means. Okay, so now the proof of this. Let n denote the cardinality of x and also the cardinality of y. That means n is the number of elements in both x and y, and we have already seen they have the same number of elements. Let n denote that thing. Now, since y has n elements, there will be a bijection which in fact comes directly from the definition of finiteness of y and the fact that it has cardinality n. There exists a bijection because G has already appeared here, so let us write H. From this set onto Y. What this bijection H precisely is, we don't know, but at least there is one. In fact, that's what it means for Y to have n elements. Okay. Now note that H is a bijection from this set into Y, and G is a bijection from Y into X. So we can take the composition of G and H to form a bijection between this set and X. Then the following composition is a bijection, because we are going to now compose two bijections, so it will also be a bijection, G and H. G and H. So which one shall we write first? G. G composition H. It's because I have been doing algebra for quite a while now, that I have got used to writing arguments of function on this side, following Herstein's topics in algebra notation. So I got a little confused here as to what should I write, G composition H or H composition G. But clearly we have to write G composition H, because when you calculate this, or rather let me write I here, then first H takes us from this set to Y. That means H of Y, H of I is an element in Y. On that it makes sense to apply G. So that's why G composition H. So now this is onto x. Now see, this is the bijection between this n element set and x. So we can use this bijection to write the, where is it, this sum as a finite series. Then I will vary from 1 to n, and in place of x we are now going to write the bijection value at I. That means G composition H of I. Remember, here we have just simply used the definition of this finite sum. Okay, now this composition clearly is just simply G of H of I, and that thing equals F composition G of H of I. Okay, now what is this composition now? F composition G. We have taken this composition simply because F and G appear in that manner. So let's recall, F was a function from x into R, and G was a function from y into x. In order to form this composition, it does not matter that G is in fact a bijection, but this thing matters that G takes us from y into x and then F takes us from x into R. So that means this composition takes us from y into x via from y into R via x, and that's why this composition just simply is a real valued function with y as domain. So now if you apply the definition of finite sum again with this real valued function, with this finite set y, and with this bijection between y and this n element set, then this finite series will be equal to this finite sum. Which you can clearly see why that is so. It may be a little confusing to come from this to this, so you can think of going from here to this one. In order to write this, what the meaning of this sum is, what do you need? You need a bijection between y and such an n element set, and such a bijection is here we have H, and you need a real valued function from y into R. This is that real valued function, F composition G. So just applying the definition of this sum, you will have this. That's just it. And this thing is nothing but f of g of y. Oh, sorry, y. So that's what we wanted to show. This sum equals this sum. They have the same value. Then we have part D, which is substitution 2. Substitution part 2. So let's recall the statement. Let n and m be integers where n is less than or equal to m, and let x be the set x equal to the set of all integers I lying between n and m, including n and m. And we need a function also. Function means we need some real numbers corresponding to the elements here. Let ai be a real number assigned to each integer I in x. Then we can of course consider this finite series where the index varies from n to n. That series will now be equal to this sum over x. X is clearly a finite set which you can see, so this sum makes sense, but still you may be a little confused about having a I here. Usually in this type of sum you have f of I, some function evaluated at this variable I. This ai is in fact a function which maps I into the real number ai. That's just it. Instead of writing a of I, we have decided to write this as ai, a suffix I, because that's how we write the values of a sequence. In this case we are dealing with a finite sequence, of course, because the function that we have, that we see here, whose value at I we are writing as ai, is a function from a finite set into the set of real numbers. Anyway, so let us now prove this. So again we will need a bijection, but before that let us proceed like this by, now this is where we start using lemma 714 results, its parts where we have elementary properties of finite series. So we can use them at to our advantage. By lemma 714 part B, this series can be changed slightly like this. It is varying from n to m. We can now make it vary from 1 to m minus n plus 1. This will be j minus okay, so it will be the opposite, j plus n minus 1. You go to part B of this lemma and you will understand what we have done here. The sum remains, rather the series value remains the same. We have just tweaked the index I. In its place we have written j, and now j has a different lower limit and a different upper limit, and here also we have changed things. Now consider the function because we have j here, so it's a good idea to write j, and j varies from 1 to m minus n plus 1 into x. But what is the precise function? G of j is defined to be equal to j plus n minus 1. That is what we have here. Remember that x is this set. So in this case, it's not that obvious that this function is a bijection. You have to prove it, and that part I leave to you. One can show that f means g. I am talking about g. One can show that g is a well-defined bijection. Hence, now do we have to just simply use the definition? m minus n plus 1 a g of j, which equals summation ai, where I varies over x. You can probably understand why we changed from this series to this series. It's because when we define the, when we use the definition of such a finite sum, we have a series where, according to our definition, the index starts from 1. Okay, so that's why we conveniently changed this series to this. Same thing, but another way of saying the same thing. And that's how you have the proof of part D, the second substitution also. Next, E. It will be a good idea to refill now a little. Next, part E, where we have two sets. Let x and y be disjoint finite sets. Unlike that one, in part C, here x and y don't have the same cardinality necessarily. We don't have anything to do with their cardinality being related in any way. They are just simply finite sets, but it's given that they are disjoint. They don't have anything in common. That is, their intersection is the empty set, and there is a function. From their union into the set of real numbers be a function. Then this is true. The sum of the functional values as z varies over x union y equals this finite sum as x varies over x plus this other finite sum as y varies over y. Okay, so now we will prove it. In the proof, we will okay, let me just write what we are going to write now. First of all, for the sake of notational simplicity, we are going to denote the cardinalities of x and y by some symbols, say n and m. Let n denote the cardinality of x and m denote the cardinality of y. So x has n elements and y has m elements. Now there exists a bijection because x has n elements. let us call it G. From this set into X, and one can easily set up a bijection which we can call, say, H, F, G, H. N plus M into Y. Note that existence of such a bijection comes directly from the fact that we are simply denoting the cardinality of X by N, and hence the fact that X has N elements. However, existence of a bijection like this is not simply the definition of Y being finite and having M elements, but one can use the fact that Y is finite and has M elements to set up a bijection. I leave the task of actually defining a bijection like this to you. It's very easy, it should come naturally to you. However, if you don't get this or anything else that I have left to you, you are free to ask me. Okay. Hence, by parts C and D, what did I have here? It's a little difficult to write things prematurely. I mean, after writing something down only we realize, okay, we have used this part and that part here. Anyway, let me just write hence by part C and part D. Whatever I have hastily written down here is whether it's going to be correct or not. Let us see. Hence by part C and part D, we have so I have written down the first sum and the second sum as series. So the first sum, writing the first sum as a finite series is just the definition of this sum using this bijection, f of g of I, where I varies from 1 to n. There is no mystery in this is just the definition. And what about this other sum, f of y, where y varies over y? In its place we have first of all written that this thing is equal to the f of h of I, another sum where do I have space for writing this? N plus 1, n plus m, and this sum in fact equals this finite series. F of h of I, where I varies from n plus 1 to n plus m. Okay, now here it seems like we have done many things. So what is it that we have done, and how are parts C and D being used? We can clearly see that neither part C nor part D has been used in writing this sum as a finite series. It is just the definition, but that means we have used the parts here. Part C is our first substitution, where we have a finite set x and a real valued function f from x to r, and there is a bijection g from y to x. Then this sum becomes equal to another sum where in place of y we have it will look somewhat confusing because we have y here, no? Okay, but you can still understand what is going on. In the original part C statement, we have the sets x, r and y and the functions f and g in this manner. F is a real valued function, g is a bijection between x and y are finite sets. Here, however, in place of x, we have y. Okay, so that is because this is our original sum, and this y is a finite set having m elements, and the role of y now is being played by this set, which also has m elements, and in fact there is a bijection between this y and this set, and that bijection is your h. So that means h is playing the role of g here, and f is like before f. So that means what the part C says is that this summation of f of x as x varies over x is the same as summation of f of g of y as y varies over y. That means now summation of f of y as y varies over y, think of this y as capital X, will be summation f of what is the bijection between this y and this h, that is playing the role of g. So h of I, in place of y we are now writing I, and that I varies over our new set, that is this set. So these two sums have the same value. So in this step we have used part C, and where have we used part D? We have just simply used part D in writing this thing in place of this, and you can clearly see how. So I'm not going to say anything more on that. So this is where we now stand. Okay. So we have written the first sum on the right side as a finite series, and we have also been able to write the second sum as a finite series, this one. So now we can add them up. Adding them up means adding this two finite series, and here we are going to again use one result from our lemma 714, so that can now be used conveniently. I think it is the first part A itself. Yes. Now, by lemma 714 part A. Oh, okay. Not so fast. I am in fact unable to apply this lemma, not yet. Before that, I need to make some more changes. You will realize why. Now note, let us again go back to our bijections. We have these two bijections now, G and H. Now because X and Y are disjoint sets, hence these bijections can now be used in a very straightforward manner to set up a bijection between X union Y and one such set. Since X and Y are disjoint, the following function is a bijection. And the function is, let us call it K. Where K is defined like this. K of I is defined to be equal to G of I if I varies between 1 and n, and is defined to be equal to H of I if I varies between n plus 1 and n plus m. Saying this is saying a lot, in fact. It may be easy once you see why this is a bijection, but keep in mind, when you say some things like this, you in fact have to prove it. It's a different matter. You may not choose to show it in your solution, but you should have the proof with you of everything you say in mathematics, so that if someone asks you, how is this true? You should be able to provide them with the proof. Okay, so this part also I leave to you. You are supposed to fill in these gaps. You should be able to see and in fact prove to yourself rigorously, hopefully, that this K in fact is a bijection, and that fact rests on these facts that G and H are bijections and X and Y are disjoint. Now I am in a position to use lemma 714 part A. So by lemma 714 part A, summation f of x as x varies over x plus summation f of y as y varies over y equals equals the first sum by definition is this series f of g of I, where I varies from 1 to n, and the second sum we have shown equals this series f of h of I, where I varies from n plus 1 to n plus n. And in this next step we are in fact using this lemma 714, and where we of course will merge these two finite series into this single finite series. But if I directly write this, it may be somewhat still a little confusing, so let me write another intermediate step. Okay, what have we done here? In place of g we have written k, in place of h also we have written k. That is because that's how we have defined k. In this part of the range of I, k of I is g of I. That's what k of I means. But when I varies from 1 to n, g of I is by definition k of I, and when I varies from n plus 1 to n plus n, h of I is by definition k of I. And now we are using this lemma to merge these two sums into these two series into this single finite series, where the index varies from 1 to n plus n. Okay. Now the fact that this k is a bijection does not play any role in this step. It's simply that the form of this sum allows us to write them as a single series. Now the fact that k is a bijection will come into play, and also that simply because k is a bijection from this set to x union y, it tells us also that x union y has cardinality n plus m. So using the definition of finite sums again with this bijection k, this series in fact is nothing but this sum. Okay, so that's how this sum equals the sum of these two sums. You can understand why this is equal to this, or if that feels somewhat confusing, you can go from here to here, from the symbol to its meaning. In order to write this as a finite series, you need a bijection between x and x union y and one such set, which we have, and that is k. So that's why this sum equals this. So that proves part D. Part D or part E, in fact, we have proved. And the other parts I am going to leave the proofs to you, which are in fact easier than these things. Parts F, G, H and I. Yes. Easily follow from parts, follow from the corresponding parts of lemma 714. We can write like that, but it will be a little vague. Let me give you the actual correspondence. Which one follows from which one? so that you can write the proof for yourself slightly more easily. From parts C, D, F and E. E of lemma 714. So this completes the proof of proposition 7111. So now we have all these properties of finite series with us. But please you complete these things, okay? Whatever I am not doing, you please complete them for yourself. And let us solve one more. This next one, in this one we are just simply going to write some statements, and here I am going to be in fact more sketchy. I will not prove anything. There is a reason. Form A so here we have been asked to in fact define something. Form a definition for the finite products. So now we are moving from series to sums to products. So for sum we use this summation notation which comes from your Greek capital sigma. For product we use Greek capital pi. Product of AI, where I varies from say 1 to n, where n is some integer, and AI is of course some real number. It's usual, just like series. And this product over set, where X is a finite set. Parallelly, just like what we have done so far for sums, we have to also do for products. Which of the above results for finite series have analogs for finite products? Analogs for finite products. Note that it is not hint but a general warning. Note that it is dangerous to apply logarithms. Because some of the AI or f of x may be 0 or negative and also because we haven't defined logarithms yet. If one is faced with this task of doing everything, it seems a little daunting, because we have seen that there are so many things with finite series and then finite sums. Then if one, after having gone through all those things, if one is then faced with this task, then one may feel, oh, again we have to do those things. So one may come up with the genius idea of using logarithms to define products, because of this rule that we have come across in elementary school. Logarithm, there at some stage we are introduced to logarithms, right? Or rather, logarithms are introduced to us. We come across a thing like this. So you may be tempted to define product using sum and logarithm, but that cannot be done because there is the danger of having these ai's of the f of x values being 0 or negative. Log 0 is undefined, and if you take logarithm of a negative number, a negative real number, that usually is not defined in real analysis. For that you have to go to complex logarithmic functions. So and anyway, besides, we haven't yet defined logarithms. Okay, so following the rule of this text of not using anything that has not been defined, we have to do it from scratch. So that is why I will leave the proofs to you, which are in fact exact copies of the corresponding of the proofs of the corresponding result for finite series and finite sums. So in this solution, we will just simply define these symbols, and we will write the statements for the results corresponding to lemma 714 and proposition 7111. So we start off like this. Let ai, where I varies from m and m to infinity, be a sequence of real numbers. So here what I am doing is that if you go back to our first video on these exercises, there we have rigorously defined the notion of finite series. In the text also there is a definition, but as we saw, there were some issues in that definition which we addressed in one exercise. So just like that, we are now going to define products. Let this be a sequence of real numbers, and define a function f from the Cartesian product of the system of natural numbers, or the set of natural numbers and the set of real numbers into the set of real numbers by while defining a finite series, we defined this function slightly differently. We wrote r plus this, but now because we need product, so we are defining like this. Then by the principle of recursive definition, or rather more specifically by that discussion at the end of an exercise, if you recall, there exists a unique function g from n into r, that is, g is a sequence of real numbers. G itself is a sequence of real numbers. Its domain is the set of natural numbers, such that g of 0 is am and g of n plus plus, instead of writing plus plus, we write n plus 1 is equal to f of n comma g of n for all n belonging to n. The existence and uniqueness of this function g comes from that exercise. We then define this product ai to be equal to g of n minus m if I don't have a space for writing if, so you just take the inequality condition. And unlike the previous case, in case of a finite series where we had 0 here, this time we will have 1. Okay, so this is the definition of a finite product. Now, just like before, one can show that this rather strange looking, artificial looking definition in fact gives us the notion of a product that we would like a product to be, that matches with what we know as a product. One can see that the product is equal to 1 if n is, I hope I don't mess up this n and m. Yeah, m is the lower one, n is the upper one. If n is less than m, and if n is greater than or equal to m minus 1, then the product of ai, where I varies from m to n plus 1, equals I varies from m to n times a n plus 1. Previously we had sum, and here plus. Here we have product, and multiplication, again product. Okay, so these things can be verified, which I urge you to do. Just like with finite series we did these things, with finite products also you will see that you get these things. Okay, so this is our definition of a finite product. And now we are going to state, below we state two results. Like lemma 714 and proposition. Okay, but for proposition 7111 we again have to define products of over finite sets. So let's just do this one first. Without proof. So this is, I am just simply going to call it result 1. So we are now just going to write the things corresponding to the finite series results. Let m less than or equal to n less than p be integers, and let ai be a real number assigned to each integer I lying between m and p. Then the product of ai as I varies from m to n times the product of ai as I varies from n plus 1 to p is equal to the product of ai as I varies from m to p. You can see why we are not proving this. The proof will be exactly like the part A of lemma 714. Then B, let m less than or equal to n be integers, k be another integer, and let ai be a real number assigned to every integer I lying between 1 and n. Then then the product of ai as I varies from m to n is equal to the product of a j plus m minus 1, where j varies from 1 to n minus m plus 1. Have I written it correctly? Let me see. And yeah, wrong. What I have written doesn't make sense. This is not the one. It's that one where we subtract k and oh, I have not used k at all. How can I write the correct thing? Subtract k here and add k here. N plus k. I was trying to remember, but I messed up. C left this be integers and let ai, now we have two sets of real numbers, b real numbers assigned to each integer I lying between m and n. Then product of ai bi as I varies from m to n is equal to product of ai as I varies from m to n times the product of bi, where again I varies from m to n. Part D, let m less than or equal to n be integers. Let ai be a real number assigned to each integer I lying between m and n, and let c be again a real number, also a real number. Recall that these parts c and d correspond to those parts which are named linearity in lemma 714. Here, however, there is no linearity or anything. Then the product of CAI, where I varies from m to n, is equal to okay, so I am noticing something now. Only C will not come out, no? Because each term in this product has a C with it. So how many C's are there? N minus M plus 1. Am I right? I can write M as 1 plus M minus 1, then N as now what okay, why am I getting confused here? Say M is 2 and N is 4. So how many terms are there? 3 terms. 4 minus 2 plus 1, yes. N minus M plus 1 times product of AI as I varies from M to N. Do we really get the number of terms, number of C's in this product equal to N minus M plus 1? You may be a little doubtful about it. What happens if, say, our M is minus 4 and N is minus 1? There are 4 terms here, and minus 1 minus minus 4 plus 1 is what? This minus 1 and plus 1, they cancel each other and we are left with 4. Yes, it's in general true. It does not depend on the signs of N and M. And if you are still doubtful, you can take a positive N also. You will see that you get the number of terms. E. I did not notice this thing before. I was just simply again and again writing simply C here. It just shows that how careless we can be, and this carelessness is of course a little excusable simply because the things we are going through is a little boring and have a certain sameness to them. There is nothing interesting. These are the kind of things that you go through only once in your life. So that's why when you go through these things, go through it carefully, and that's just it, so that you don't have to again come back and look at it. That will be extremely boring. Then E, let this be integers and let AI be a assigned to each integer I lying between M and N, of course. So which one is this? Oh, it is just simply okay. Then the absolute value so we have already reached part E. That is nice. This ordeal will be over quick. absolute value, as you can see, does not behave so nicely with sums, but it behaves extremely nicely with products. And finally, we have part F, which is the monotonicity. Suppose these are integers. Let ai comma bi, we need two sets of integers again, b, two sets of real numbers, sorry. Suppose also that ai is less than or equal to bi, and we need that thing also, because we are going to multiply these things now. Not just simply these inequalities, but these, that they are not just any real numbers. Here also we could have simply mentioned, I forgot, these are non-negative real numbers. But this means the same thing. For all I varying from m to n, then okay, so these are the things that we have which turn out to be true about finite products that we have defined. And this is the statement of result 1. The proof, if you want, you can, I hope you do at least convince yourself that each one of these results, each one of these parts is true, is in fact true. Don't just leave it like this. But the solution ain't over yet. The next thing we need to do is we need to then use these finite products to define products over finite sets, and then state a result corresponding to proposition 7.1.11 about this type of products, which of course I am not going to do today. We will do that in the oncoming Sunday. So that's it. I am ending the video here. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. Tomorrow we don't have any upload, and day after tomorrow, as I promised, we are going to see graph theory instead of our usual field theory. Field theory we will do afterwards. So we will actually we are going to see what these graph minors, contraction, topological minors, what these things are. So see you on Tuesday. Until then, have fun with mathematics and keep asking questions. So that's just it. So until then, this is me, the devil from a mathematical room. Have a nice night.